Hi everyone, welcome to Coding Mazes in Delphi and C++. My name is David Millington, I'm the C++ Product Manager at Embarcadero. I speak both Delphi and C++, but this talk uses both, so it will show code in both languages at once. I am Australian, but I happen to live in far north Europe, where right now winter hit a few weeks ago. I have to stay indoors and do programming. So we're going to talk about some basics about generating mazes. This is something that's been a weekend project of mine for a couple of weekends. I found it really fun. I thought it'd be something to share with everyone else. So we'll cover what a maze is and what do we want to build. Some concepts like grids and cells, a few algorithms to generate a maze, and cover solving mazes as well. So once you have a maze, how do you go between the entrance and the exit, say, or between any two arbitrary points? How do you do that and find a solution? So we have code snippets in both C++ and Delphi, and I have written the same application in both languages and can give a live demo showing some of these algorithms work and do their thing. So a maze, basically a set of twisty passages and connections, such that usually any location can be accessed from any other, although it's difficult to trace the path how. Now they don't have to have an entry or an exit, those are usually actually arbitrarily defined. And in this talk I always use the bottom left as one point and the bottom right as another. Now I've been fascinated by mazes for a long time and I really enjoy solving them. But I didn't really know how to generate them. I had a few sort of ideas, but I had never sat down and actually tried to do anything until quite recently. And they're actually remarkably easy to generate and solve, and you will be able to generate them and solve them after this talk. So there are two classes of algorithm, building paths and building walls. And the ones I'm going to discuss today only build paths. So to do that, we start with a grid of cells, which you can see on screen. Here there's a 4x4 grid. Every cell has a few neighbours, but none of those neighbours are linked, that is, there's a wall. So you build a maze by linking cells, that is, destroying the wall, but in code we are linking cells. So a cell knows it is connected to another cell, and that's visualised as not drawing the border between them. That creates a path. So the maze is not the black lines. The maze is the white area in between that will become a series of connected squares. So let's demonstrate this. This is a really bad maze generation algorithm. It only knows how to connect cells that are labelled with letters of the alphabet in order. So each cell knows its neighbours, and it wants to choose one of those and say there is a link to this neighbour. And in this particular algorithm, the algorithm only knows to look for a neighbour, which is the next letter of the alphabet. So we have some cells here labelled A, B, C, and D, and so we're going to connect A and B. And when we do that, you can see that the wall between them vanishes. Next, we connect B and C, and again the wall vanishes. And after this, we're going to connect C and D, and again the wall vanishes. And you can see that this is starting to look like a path or a maze. We have a curved and twisty path already. So this indicates having cells in a grid, and what happens when you link a cell. That is the difference between a cell having neighbours and a cell having linked neighbours. So we do this a few more times and we get a maze. This one's quite small because it's only a 4x4 grid, but you can see that despite that, it is recognisably a maze with interesting shapes and passages. Building a maze is the process of making these links to form paths, and different algorithms will form these links in different ways and give different looking results. A few interesting bits of terminology here, like rivers, which is where you have really long paths. But some of the different sort of shapes or texture that you'll get mazes with curly paths, with lots of branches, with few branches, with lots of dead ends, with very few dead ends, and so forth. So some algorithms are truly random, but others make mazes that follow a structure that you can sort of see on screen. And the way a maze looks is called its texture. And if an algorithm tends to produce a particular texture, it's called biased. And our first algorithm is a very simple one, and it is very heavily and badly biased. It is not a good algorithm. But let's have a look at it. Before we do that, I'm going to show some code snippets for grids and cells. So before any of our algorithms, we need a grid that holds cells. Those cells need to be aware of their neighbors and need to be able to link to their neighbors. And we need to have enough properties and methods so that an algorithm can move through the grid, can visit the cells and link them. So let's see some code. Delphi on the left and C++ on the right. So grid is basically a container of cells. It has a number of rows and a number of columns, and you can ask how many rows and columns it has. It lets you get access to any cell at a particular row or column. It has a certain number of cells, and it also gives you a random cell if you ask it. This is useful for some algorithms. And it's also useful to be able to enumerate over each row. Each row then contains a list of cells, or to enumerate over every cell, not worrying about rows or columns, but you just want to get every cell in the grid. We also have a repaint method, so you can represent a cell size in pixels. A cell might be 50 pixels big or 100 pixels big. And here, in this particular code, it returns a bitmap. Now the grid owns the bitmap. It's just that this method gives you access to the bitmap that it just painted. Now in Delphi I'm using interfaces. You can see iGrid and iCell. These are reference counted. In C++ I'm using shared pointer, which achieves something quite similar. So the grid owns all of the cells. Now let's look at the code for a cell. First is that we need a direction. This is the relationship that cells have to other cells. They're their neighbors. So that could be north, south, east, and west, which on screen is up, down, right, and left. Now a cell exists at a particular row or column, and it knows where it is. Now you can link it to another cell, or you can unlink it. You can get a collection of links, that is, a collection of the cells that are linked to this particular cell, or you can check if a cell is linked. And you can also get a list of all the neighbors, so that is, all the cells in any one of those directions, north, south, east, or west, whether they are linked or not. Finally, there's a distance property, and distance is going to be used later. It's basically just an arbitrary number that we happen to call distance that we assign to every cell. So a few things to note here. For Delphi, I'm using the Spring collection, Spring4D. Spring4D is a fantastic library. The collections in it are only a small part of it, but they are fantastic, and I strongly recommend that you investigate using them. For C++, I've gone a bit overboard using shared pointers everywhere and so forth, but I think it can be useful. Now, one interesting thing is that shared pointer, much like an interface in Delphi, is ref counted. And if cells keep connections, they keep references to the cells that are their neighbors and their links. Here, the public interface uses shared pointer because when you want to get a cell back or a list of cells or so forth, you want to know that they all exist. But cells should not control the lifetime of other cells. The grid is the owner. And so internally inside the cell class, which I'm not going to show you today, internally it uses std weak pointer, which you can get from a shared pointer. And a weak pointer can go out of date. It can expire when the item that it points to, whose lifetime is controlled by the shared pointer, when the item that it points to is freed. for Delphi using interfaces that are also ref counted, and there's other code that I haven't shown on screen that looks after the same problem. So let's look at some algorithms. We generate mazes by visiting cells. It's called walking the grid. And the pattern of where to walk and when to link, and where to link where, is what creates the maze. And algorithms do this in a whole variety of different ways. So we're just going to look at three. They are binary tree, which is a simple and quite biased algorithm. Aldosporoda, which is a random walk algorithm. There are a number of different random walk algorithms. This is one of them. And recursive backtracker, which is a constrained random walk algorithm. And each have different behavior. So let's look at the binary tree algorithm. It is very simple. You have a grid, and you can visit the cells in any order. In the graphics that I'll show in a moment, I think it goes bottom to top, left to right. In the code I wrote, I think it goes top to bottom, left to right, but you could just pick them randomly, and it really doesn't matter. You just need to visit every cell. And at every cell, you randomly either link north, that is upwards, or link east, that is to the right. If you can't link east, then you link north. If you can't link north, then you link east. If you can't do any of those, then you do nothing. And there's only one cell where that's the case, which is the top right cell. The top right cell cannot be linked to the right or to the top because it has no neighbors in those directions. So I'm going to use a little queen symbol here, the chess piece queen, because a queen can move pretty much everywhere. I think it's symbolically nice. And this indicates the current cell that we're looking at in our algorithm. So we start on the bottom left. That doesn't matter where, but we're going to start on the bottom left. And we randomly decide to link north. Okay, so let's just move to another cell. And then we will randomly link east this time. We'll move to another cell. And we will randomly link north this time. Now we'll move to another cell, and at the rightmost one, the choice is no longer random between east and north. It can only link north. Now all rightmost cells and all top cells can only link either upwards or right. So that means that this algorithm is going to give two large, completely empty paths. The other thing about this algorithm is that overall it's going to tend towards an up and right pattern. That's because it only chooses between linking up and right. So here's some code. The code is very simple. For each cell in the grid, it finds out if it has a neighbor to the north and east, and if it does, then it stores them. Then, of those neighbors, maybe 0, maybe 1, maybe 2, it picks one randomly and it links to it, and that's it. This is very, very short code, very simple. And we end up with something like this. So you can see the texture here. You can see that this looks, when you look at it on screen, it looks kind of square and jagged, and it seems to have this flow from the bottom left to the top right. And you can also see how at the top edge and the right edge, there's a full row and a full column of cells that are completely connected. And that's because the algorithm didn't have a choice about what to connect. So that's an example of a maze texture. Now texture can be interesting to visualize and quite useful to visualize. Let's talk about visualizing texture for a moment, and we're going to do that with a distance algorithm. So let's assign each cell a number based on how far it is from the starting point. And again, the start in a maze can just be an arbitrary position. But I use the bottom left corner of the grid. So we're going to assign that cell in the bottom left the number 0, that is its distance. It is 0 distance from itself. The algorithm is pretty simple to calculate the distance. We just walk, and of the neighbors from a cell, every cell just has a distance that is 1 more than the last one, unless you happen to find a cell that already has a value because paths intersect. So let's start. The distance is 0, And then it only has one neighboring cell above it, and so that cell's distance is one more, which is 1. Now this cell has two neighbors, one above it and one to the right, and both have a distance of 2. Now that path ended, it terminated in a dead end, but there is one path still remaining, and this path has 2 neighbors to the cell. Both of those have a value of 3. And you can continue this by traversing the path, by walking the path for the entire maze. So what happens when we apply this to the maze that we saw earlier? Now you remember this maze, it has a certain texture, and we want to use the distances that we just spoke about to visualize the texture. Well, first of all, let's just calculate the distances. And we get something like this. Now, numbers by themselves aren't particularly useful, but you can see how, if you start from the bottom left, you can track how the distance is calculated. And the furthest away cell is, I think, about 40 cells, 40 steps. And that's in the bottom row, about 5 from the right. But numbers for a human aren't really very easy to visualize. But what if we assigned cells colors based on these numbers? You have a color scale from 0 to whatever the maximum is, let's say that's 40, of grey to red. And then you could visualize the distance from the starting cell by the intensity of the color. And that looks like this. And straight away you can immediately see the texture. What's particularly obvious is how leaving the starting cell requires going up and to the right always. Now this is also useful for solving mazes because you can pick an endpoint and work backwards. Any neighboring cell with a smaller distance is going to be closer to the start than the cell you are currently in. I always use the bottom left as the start of a maze and the bottom right as an endpoint. So we want to solve in the reverse to these arrows. We want to go from the end back to the beginning. That is, from the arrow on the right back to the arrow on the left. So once we've calculated the distances, this is quite simple. We start with the exit cell, the cell that we regard as the endpoint, and that's the one on the bottom right that is highlighted. It has a distance of 36, and we want to pick the cell, any cell that has a value less than 36. And it only has 2 neighbors. One has a distance of 35 and one of 37. So because we want the one that is less, we choose the one with a value of 35. And we repeat this. This cell only has, well, it has 2 neighbors, but it only has one that's of interest, and that's the one with a distance of 34. So we pick that. This cell has 2 neighbors with distances of 33 and 35, and the only distance that is smaller than our own is the one with a distance of 33. So we pick that. Now if we continue this process, we end up with a path like that. And so suddenly, through calculating distances from a cell, through walking the maze, we've realized that by going in reverse, by starting with a high distance and looking towards the lower distances, we can solve a maze. So I think that's enough slides without looking at some actual live demos. So let's actually use this to visualize the binary tree that we saw earlier. So just a reminder, the binary tree algorithm links randomly to the north or east. So we're going to run this algorithm quite slowly, and we're going to highlight the current cell that it's looking at in red, and the one that it's linking to in blue. So this is the random north or east one. And we should see a few patterns. We should see that the top row only links to the east, to the right, and the right column only links north, up, because those are the only choices. But otherwise, we will see it randomly linking upwards or rightwards, north or east. Let's run some code. Now I'm going to maximize this and give it a fairly large cell size. Create a new maze. Now we're going to use the binary tree algorithm, and we're going to visualize it with something I've called candidates, which is basically the information that the algorithm gives back. So we're going to run the binary tree algorithm on this grid. So you can see the red cell is the current one and the blue is the one it's linking to, and it's walking over all the cells, randomly picking one to the top or right to link to. On the right hand side it is always having to link up, and at the top it always had to link right. There we go, it is complete, and we have a maze. Now let's apply some of the other things we were talking about to this same maze. We can also visualize the distance from the bottom left corner as numbers. So you can see, starting in the bottom left, which has a distance value of 0, we walk through 1, 2, 3, 4, and then we have 2 cells with a value of 5, 3 cells with a value of 6. Following down to the bottom left here, we have a dead end, but following to the right and up, the distance increases. And we can visualize this with colors. You can see the bottom left cell, which is distance 0, is always painted in red, but otherwise the scale is grey through red to indicate a close or far distance from that starting cell. And we can also show the maze's solution, so picking the bottom left and the bottom right cells, the distances can find us a path between the two. So the binary tree algorithm was not particularly good. It had a number of rather strange features, such as the row at the top and the column at the right. So let's have a look at a very different algorithm. This is a random walk algorithm. There are a number of algorithms that are based around random walks. This one is called Embarcadero. And it's quite simple. You pick a random cell to start. It will have some neighbors, so you pick one of those. And if the neighbor has not been visited before, then you create a link. Then, starting at the neighbor that you just picked, whether you linked or not, you start the whole process again. Now this is completely random, but it can be slow because it can visit cells many, many times. There's nothing constraining it. There is nothing stopping it going over cells that it has already visited many times before. And if it does visit a cell that has visited before, it still picks a neighbor, but it doesn't link, it just visits and then tries again, so you can watch it just wandering around. But before we look at it, let's just have a look at some of the code. So again, this is quite a short method. We basically pick a random cell, and we want to know when the algorithm terminates. Well, the algorithm terminates when there are no cells left to visit. And so that's pretty easy to keep track of just by counting them, starting off at the number of cells that the grid has. And so while there are unvisited cells, we find a random neighbor for our cell of interest. And then we want to know whether to create a link to it or not, whether it's been visited before or not. Now, by definition, in this algorithm, if a cell has been visited before, it will have a link. So you can tell whether it's been visited by whether it has any links. And if it doesn't have any links, then we create a link to it. We decrement our count of unvisited cells, and then our cell of interest becomes the cell that we were just looking at, whether we created a link there or not. And the result of that looks like this, and I think this is a much nicer looking maze. But let's have a look at it live, because the random walk part of it is quite an interesting feature. And we're going to color the algorithm by coloring cells that have been visited blue, and the current cell of interest is going to be red. So let's have a look. So I have a new fairly small maze here, and I'm going to use the Embarcadero algorithm, and I'm just going to run this. So blue cells are the ones that's visited, and you can see the red cell is the current cell, the one that it's walking and is picking a neighbor of. And you can see that it moves in a completely random direction. This is called a random walk. And there's nothing stopping it going over and over cells that it has already visited, and you can see this happening quite a lot. But every so often it finds a cell that it hasn't visited before, and then it creates a link. This is a very slow algorithm, a very inefficient algorithm. Look at it right now. It just happens to be going over and over and over cells that it's already visited. And the whole right-hand half of the maze it hasn't got to yet. It will eventually. See now as it's starting to head in that direction. Now, even though this is a very small maze, this doesn't have a great deal of cells. This is going to take so long that I'm going to stop it. And instead I'm going to start again. This time, rather than playing and showing step by step, I'm just going to run the algorithm right through. And so we get a maze that looks like this. And again, let's visualize this. So numerically, starting in the bottom left, we can count the distance. But more interesting, I think, is to show the colors. And you can see that this one does look a lot more random. There is one sort of bright red area, which is the furthest away cells, as you would expect. But overall, this doesn't really show the same kind of pattern that the previous algorithm did, and that's a good thing. Let's look at the solution as well, going from the bottom left to the bottom right cells. As you can see, that sort of wanders over the maze a bit, and it doesn't have that same up and to the right kind of bias that the previous algorithm did. So we are improving. Well, that algorithm produced good mazes, but it did so very inefficiently. So let's look at one final algorithm, which is another type of random walk, but it is a constrained random walk algorithm. This one's called the recursive backtracker. And it avoids that slowness and the repeated visiting of too many cells. So it still tries to randomly walk, and it tries to link. But this algorithm is aware of a dead end where it hasn't got any neighbors that it can link. So it does that by keeping track of where it's been, and if it finds it's in a dead end, it backtracks until it finds a cell with a neighbor that it can link to, and then it heads off in that direction. So to do this, we use a stack to remember that path. So we start somewhere, completely arbitrary, but for me, the southwest corner. And because it's our start, we push it on the stack. So we remember where we've been and we're starting. So we pick a random unvisited neighbor and we link to it. And we push that on the stack and make it the new current cell. And we continue that, picking a random unvisited neighbor and linking to it and pushing it on the stack for as long as we can. But if there are no unvisited neighbors, then we pop cells off the stack, which is going back until we find one that has unvisited neighbors. And there's always going to be one that has unvisited neighbors until the grid is completely filled, until the maze is complete. So the code to do this, again, is quite short. We create a stack, and we initialize it with the first cell. And we keep looping while there are any things on the stack, while there are any cells on the stack, because we know that we have completely filled the grid only when we've backtracked so far that we've got right back to the starting cell. So we start with the current, which is the top of the stack, and we get all the unvisited neighbors. I haven't included the method there for get unvisited neighbors, but it's simply a list of all the cells that have no links that are neighbors of the current cell. And if there are any of those, if there are any unvisited neighbors, then it picks one randomly. It links to it, it pushes that on the stack. Otherwise, if it can't do that, then it needs to start backtracking, and it does that by popping the cell off the stack. And so that means next time it goes around the loop, it will be one further backwards. And that creates mazes that look like this, and just like the first random walk algorithm, it looks very similar because this too is a random walk algorithm, and I think that's quite a pleasant maze. So let's look at that live. And in this live demo, we're going to color the cells that are in the stack, that are in the path that it can backtrack, blue, and a red cell is going to indicate the current cell, the cell that is currently examining neighbors of. So once again, I have a maze of the same dimensions, and this time we're going to use the recursive backtracker algorithm, and we're going to run that. So you can see it is randomly walking, but it's not going over where it's been before, and blue indicates the stack. Okay, and it just hit a dead end, so now it's walking backwards until it found somewhere it could go. Once again. And now it is going to backtrack all the way to the cells on the left, and it found a cell that it could visit, and so it has started randomly walking again. And now it is backtracking completely, and it has finished. It found no cells that were unvisited, and so it backtracked all the way to the start and decided that meant it was done. So we can visualize this, again, using numeric values or colors, and you can see it has very similar texture to the first random walk algorithm. And if you want to find a solution, that is this particular maze's solution. This algorithm is much better because it is still random, but it is considerably more efficient and faster than the first random walk algorithm that we saw. So while we're here, we might as well use this algorithm to look at something a bit more complex than these very small demo mazes that are large on screen. So let's create a new maze, but let's make the cells much smaller. Let's make them, say, 30 pixels wide each. And let's run this algorithm straight away. And it creates that maze. Now, I think this maze is astounding. It is sort of long and twisty and complicated to look at. It is a thing of beauty. This is what I think of when I think of mazes. And to look at some of the distance calculations and the weightings for a larger maze, let's color this. And again, you can see some quite interesting texture there. It definitely looks a lot more random. In fact, we can generate the maze again. And we get something that obviously is a very different maze, but the texture is very similar. And you can really see the effects of the random walk. And let's try that one again, just to show an example of the kind of mazes this can create. Again, without the color, to see a maze as it would look like if you were trying to solve it. I think this maze is absolutely fantastic. Let's look at the solution going from the bottom left to the bottom right. You can see this is a very complicated maze to solve by hand. So in overview, we've looked at a few things. We've learned some concepts of grids and cells inside a grid, and that you build mazes by linking, by making paths. Now, there are other algorithms that instead build mazes by creating walls instead, but all of ours build mazes by linking. We had a quick look at bias in an algorithm and texture in a maze. Texture in a maze is the result of an algorithm's behavior. We learned how to calculate distance from a cell and then to visualize texture in a maze by coloring a maze based on distance. And then we looked at using distance to solve a maze. So given a starting point from which you calculate distance and an ending point, how to walk back through the maze to find a solution. We looked at three algorithms. The binary tree was the first one. Simple, quite bad results. Random walk algorithm, Aldous Broder, produced very good mazes, but was quite a bad and inefficient algorithm. And then we improved the random walk with a constraint on how it could randomly walk. And again, there are a number of different algorithms that are constrained random walk algorithms. This one is called the recursive backtracker. More than that, we saw them all in action, live being demoed with code that was in both Delphi and C++. Now, I mentioned this was a weekend project. I did this because I randomly found this book mentioned on Hacker News called Mazes for Programmers. And this is a fantastic book. I can't recommend this enough. So the talk today just covered a tiny fraction, but the book itself covers all these concepts far better explained and in far more detail than my talk. It covers more algorithms, much better algorithms, more advanced algorithms. But then it gets onto some truly interesting things. It talks about grids that aren't square, so cells that are hexagons or triangles, or grids that are in a circle. It talks about braided mazes where there are no dead ends, or woven mazes where you can have overlapping tunnels. It talks about putting mazes on cylinders and spheres and even a Mobius strip, and more, much more. This still is not everything that the book covers. And one thing I really want to emphasize is just how much fun I've been having just coding this up. Reading the book by itself is fun. Going through the code and writing it up in Delphi and C++ has just been so much fun. I've been having a blast the past couple of weekends doing this, and that's why I really wanted to do this talk, just to share the fun I've been having and to share this book with you as well. I'm not affiliated in any way with the author, James Buck. I just happened to come across the book and think it's absolutely fantastic. So you can find the book at mazesforprogrammers.com, and the author was interested in mazes and collecting different algorithms and source for a long time before he wrote the book, and he also has a website with source as well. And on GitHub you'll find that a lot of people have implemented the algorithms in the book in a lot of languages. So far as I know, there is some C++ code and there is no Delphi code, and I plan to put up my C++ and Delphi implementations on GitHub sometime soon. Just a reminder, mazesforprogrammers.com is that book. The Delphi and C++ source will be on GitHub soon. I'm David Millington. You can see my email address there. You're welcome to email me at any time. And with that, we'll hand over to Q&A.